Hello, and welcome to a Planetary Physics crash course. Before getting started, just as a disclaimer, today's crash course will in no way get near the true beauty behind the inner workings of the movements of the heavens. So in other words, viewer discretion is advised. If there are any physicists in the room, please escort them out now. Anyways, without further ado, let us begin. So, I begin by asking, what do falling apples and orbiting planets have in common? Well, according to Newton, gravity. More specifically, a force of attraction which exists between every particle with mass in the known universe. And this ugly duckling of an equation is how we go about calculating that force. Regardless of its looks, we shall divide and conquer and obtain full mastery of the power hidden behind these symbols. Let us begin with ma multiplied by mb. This simply refers to the masses of, let's say, a particle A and another particle B. And the force of attraction between these two particles is proportional to their masses multiplied. Now for the denominator, d squared. The d simply refers to the distance between particles A and B. This distance, according to our other friend Pythagoras, can be calculated if we find the change in the x position. Let's call this delta x, and the change in the y positions. Let's call this delta y. Once we have delta x and delta y, we can find the distance by taking the square root of delta x squared plus delta y squared, and voila, we get the distance between particles A and B. And finally, our last symbol in this equation, g. G is simply a constant that you may take as given, whose value is 6.7 times 10 to the negative 11th power. If the viewer wishes to know more about where this constant came from and why it's that value, then I encourage you to take this journey. But alas, the rest of us will not be joining you today. Anyways, that's it. That's what this ugly duckling of a formula had to say about gravity. But this is how you might see it in a physics or mathematics textbook. But as programmers, this is our form of Newton's law of gravitation. Okay, this is cool and all, and not so ugly anymore. But why do you care, dear viewer? And more specifically, how can you use this for NBody? And to that I say, good question, let's find out. But before moving forward, it will be in the viewer's interest to know of Newton's other law, his law of motion. And yeah, I know what you're thinking. How many laws did this guy have? Well, a lot. There wasn't much else to do back then, you know? Anyways, this is his law of motion. Because without motion, how can we get the ball rolling? Or in this case, planets orbiting. This formula relates the force on an object to its acceleration, which the acceleration is then multiplied by its mass. And the acceleration part is the important bit that you, dear viewer, will be greatly interested in. As another quick aside, it will be useful for the viewer to note that thus far we have been calculating the force directly between the particles of interest. It will be useful for the viewer, however, to know how to decompose the force into its x and y components. And to do so, we follow the formula that goes as follows. First, calculate the force between the particles using the original formula for F. Then, to get the x component of the force, multiply F by the change in the distance between the particles in the x direction, in other words, delta x, and then divide by the distance d. If your memory is foggy as to how to calculate this distance, feel free to go back and refresh your mind. I shall await your return here. Likewise, we can get the y component of the force by multiplying F by delta y and then dividing by the distance d. As a quick aside, delta y and delta x are simply changes in the x direction and the y direction respectively, meaning that they may potentially be negative depending on the positions of the particles in your coordinate frame. Long story short, do not take the absolute value of said changes in position in each respective direction. Alright, now to the good stuff. Let's begin by adding a bit of complexity to our lives, because what is life without complications? Let's say we have 3 particles in our universe. Let's call them A, B, and C. Actually, since we're going to be dealing with these guys for the rest of this story, let's give them some nicer names. How about Sun, Earth, and Mars? Yeah, now that we've all gotten fully acquainted, let's continue onwards. So according to our friend Newton, there exists an attraction between each pair of these particles. What does that mean? Well, let's take a closer look. Specifically, let's take a look at Earth. According to Newton, the Sun and the Earth are attracted to each other. Likewise, Mars and Earth are attracted to each other. However, as a terrestrial being yourself, you may be aware that Earth does not sway back and forth normally, unless you live in California, in which case, that's not normal, guys. Anyways, what ends up happening is that as Earth is tugged on by the Sun, Earth is simultaneously being tugged on by Mars. There thus ends up being a net force on Earth. How do we go about calculating this net force? Well, we begin by simplifying our lives a bit and considering only the Sun and Earth first. We calculate the x and y components of the gravitational force between these two particles. Let's call them Fxs and Fys, respectively. Then we consider Earth and Mars. Repeat the process and calculate Fxm and Fym. Then we put it all together by adding the x components of the forces to get the net force in the x direction. That is, we add Fxs and Fxm. And then likewise, to get the net force in the y direction, we sum up the y components of the forces. Once we have the net force acting on the Earth, we can then consider the next particle, let's say the Sun, because even the Sun is being tugged on by Mars and Earth. Likewise, we continue on to Mars and calculate the net force on Mars as it's acted on by the Earth and the Sun. Now that you have the net forces of each of the particles, what happens next? Well, the goal is to get the planets moving. So what else but to use Newton's law of motion? Through Newton's law of motion, we can calculate the acceleration, which we can then use to solve for velocity. And once we have velocity, we can finally calculate position. And what next? Well, now the clock simply ticks. One may even say that the time has stepped forward. The time step, interesting. Note that before updating the position of the particles, the net forces were calculated first. In other words, we did not calculate the force on the Earth, update its position, and then calculate the force on the other particles. Just keep this in mind as you work on NBody. Anyways, that's it. You're ready to craft your own world, and of course, feel free to stop by office hours if you have any more questions. In the meantime, go forth and conquer, and I wish you the best of luck.